So, welcome to this How to Use TF in the ROS Infrastructure 101 course. So, if you feel the need to know how TFs work or just know what are those TF, what is this TF concept, or you have a robot and you have to publish the TFs with a ROS infrastructure, then this course is for you. So, to start the course, you have to go to theconstructsim.com and from there select the Robotic Night Academy. It will pop up this new web page and you'll have to sign in if you have used our courses or done other courses with us, or sign up for free. It will pop up this page. You'll just have to sign up or log in and you're good to go. It will pop up this web page where you can select any of our courses that we have in this moment right now. So let's get started. If you click Start Course, you'll get something similar to this page where you have an IDE, a web console, the simulation, and a ePython notebook, where all the course is explained with exercises and examples. So let's get started. So, why do you need TF? Well, any physical system, especially robotic systems, have many coordinate frames that change over time. For example, a robotic arm like this one has 10 or 20 joints and they change independently, or they change and depend on the articulations and links that are before them, their parents. This changes, and this constant change in the robot configuration makes very difficult to make calculations, and some problems arise from it. One of the problems is, for example, you have a robot like this one with a laser in the TCP. Okay, this laser is making readings. It's making readings, but based in what frame of reference? Well, it's making the readings based on the laser frame. But maybe you need those data, that laser data, in another frame. Then you have to convert the data. But that's not trivial, especially in a robot like this one. And so this is one of the applications which TF makes life much, much easier. Another application is, for example, you have multiple robots. Each robot has a GPS, or knows in a way, let's say GPS or odometry or vision, any type of localization and navigation system, and they know where they are. But what they don't know is where are the other robots in reference from their perspective. So that's another way, another thing, another application of TFs. And finally, one application that it's really used in robotics is automatic TF publishing. The thing is that robots like this, or more complex robots, you don't publish, you don't generate those TFs by yourself. Why? Because it's really complex when the number of articulations grow. So the ROS gives you another tool, some tools that allow you to make that automatically with just a definition file of how the robot links are and how the joints connect all the links. You'll see all that. So in this course, you'll learn how to publish and subscribe to TFs and publish TFs in ROS topics. you learn how to use the necessary tools to visualize all this. You'll also learn how to use the robot state publisher, which is the tool that I talked earlier, that it automatically transforms a definition of a robot into TF publishing. So it's really, really useful. And then understand a bit all the necessary elements of the joint state publisher and how it relates to the robot movement and the controllers. So you'll end up creating a simple robot, or as complex as you wish, that moves, that use controllers, that publishes in the joint state publisher, and also uses the robot state publisher to publish the TFs finally. Okay, so you'll ask yourself, okay, how will I learn all this? So we will use 3 simulations for each topic, more or less. We'll use a 3D version of the classical turtle sim. We'll use also this Pi robot, which is a fully articulated, very simple but very effective to know how robot state publisher works. And finally, we'll use the multiple Kabuki robot simulation, which will allow you to learn in how, for example, to publish static transforms through launch files or through the command line. Okay. Before starting, 2 things. One, to do this course and to understand it, I highly recommend you that you have a medium level of Python, because all the code will be written in Python. Then, although this is a self-contained course, it's advisable that you have a high level of ROS, or a basic, let's say, a basic level understanding of ROS, which you can, if you don't have it, don't worry, you can do a ROS basic course in 5 days, and you'll have not only the basics, but a medium level of understanding of ROS, how ROS works, and all that you need to do this course. You also need how to use the Unix shell, and some basic, really basic knowledge of how coordinate frames work, how transforms work, but it's really basic, and actually it's more to really understand what we're doing, but you just have to know the basics. So finally, thanks to the ROS community for doing all the ROS infrastructure, all the tutorials of TFs, and also to the OSRF, the Gazebo team, and also to the Robotics Consortium. Special thanks to Gen X, which he created the 3D model of the turtle. So thank you, Gen X. You can check him out in the BlendSwap webpage. And that's quite it. You have some resources here that you can deepen in the knowledge and understanding of the topics. And let's get started. So, welcome again. So, after you click next, you'll get this simulation, or that we have a turtle model, and we have an iRobot model, and then we have a can of Coke. Yeah. So this is like our 3D interpretation of the classical 2D turtle sim tutorials. What are we going to do? What will you be able to do after this unit? Let's find out. The first thing you have to do is copy this command, which is we are launching this iRobot follow turtle launch. So let's go in one of the web consoles, doesn't matter. You'll see that the iRobot starts trying to follow the turtle. Then let's move the turtle around. this launches the keyboard teleop, so you can move the robot around. Well, the turtle, in fact. So there we go. We can move it around. So this is what you will be able to do at the end of this unit, let's say. But you'll ask yourself, okay, but what's this have to do with TFs? Well, actually a lot, because the iRobot needs to calculate the TF and the transform that exists between this real turtle and himself all the time. And for that, you have to publish the TFs of both of them referred to the same place. So let's stop the system. There we go. Okay, so let's go to the notebook. What do you need here? What will you learn? Well, you need two things. You need a broadcaster and you need a listener. The broadcaster will broadcast the TFs of both the turtle and the iRobot. The listener will read those TFs and do something useful with that data. In this case, calculate the transform between the iRobot, again, this white disk here, and the turtle. And calculating that transform then publishes in the command vel topic of this robot and makes it move to the location. The first thing is, okay, let's see what happens. Let's have a basic understanding of the TF. What's TF? What is it exactly? The first step is, let's launch this, which activates again the publishing of the TFs, among other things. So there we go. When it says ready, you have it. Okay. Then, next step. The next step is we go here and we ROS run TF view frames. Let me see. There we go. Whoops. Sorry about that. So we have to ROS CD, then CD to the source, and then view frames. Okay. Okay, done listening. And there we go. Okay, let's stop this. Okay, so what has happened here? Well, we're using what we call the tool view frames. View frames generates in a PDF format the structure, the tree, the TF tree. That way you'll have an idea of what is the morphology of TFs. So to see it, just right click, download, and then open it in your PDF viewer, and you'll get something like this. Very simple, right? So what do we have here? Basically what we have is a world frame and then a transform from world to the turtle 1, which is the real turtle, and turtle 2, which is the iRobot. Then we have some information, for example, the publishing rate and the most recent transform number, which should more or less coincide with the recorded time. Otherwise, it's not publishing. Okay? And that's quite it. I mean, it's a very simple TF. It's the most simple TF you'll get. Let's go back. And there we have it. So, you'll get something like this. Okay? Next thing. Okay, there's another tool that it's very, very similar to this one. It's very similar. Actually, it generates more or less the same, but it's more in a real-time basis. So you can refresh it and you can see how it evolves. So if you change the system and so on. Let's have a look. So if you do, we go to this exercise 3.2.1. We are going to run this first. Run this first. That means we don't have this publishing the TFs. So what will happen here? Well, let's find out. Whoops. Let me copy this again. There we go. And nothing happens. Why? Well, because this is a GUI application, so we have to connect to our system, to the instance graphical interface, and there's no TF data received. Of course there isn't, because we're not publishing it. But you see this wheel here? We just refresh it. So if we start publishing, then we'll see it. So let's go again to our page and have a look. Let's start publishing, okay? Let's start. Okay, it's moving. Well, it's pushing actually. And then we refresh, and there we have it. What's the difference? Well, basically, what's the difference is that this is in real time, let's say. You see that it's not updating, but when you refresh it, then it updates. This tool is really useful to see that you don't have any TFs publishing or they stop publishing, because if you see, when we refresh, it continues to increment all the recent transforms. Okay, and it more or less coincides with this number. But what happens if, for example, I stop it? I stop this publishing. I stopped it. Then what happens? You see, you got one because it was in the buffer, but after that, you don't get anything. That's because, so the recorded time, it's changing, but it's not changing the numbers here. That's because you're not publishing anything. And you say, okay, then why doesn't it get the no TFs? Well, because you have the TFs, just that they are not updated. So you get the last TF there. So if you echo the TF, you'll get the last one here. So that means this also gives you the information that when you stop publishing the TFs, you get the last TFs forever and ever. That's another good information that you didn't get from the view frames, of course. Let's take another step, but another step backwards. You can also do a ROS topic echo. So let's have a look. Just ROS launch the system, and then we're going, let's see where we have the robots. I'm going to move a bit the turtle, otherwise we'll end up with the turtle elsewhere. So I'm going to keyboard teleop. There you go. Okay, let's move the turtle. A bit faster, please. There we go. More or less, about there. Okay. So we can always see the TFs in the topics, of course. ROS topic echo of the TF. Let's see. There we go. We just published one because otherwise there's a lot of information published. This is just the TF from, for example, the world to the turtle one, and has this translation and this rotation. So to go from this frame, this means that to go from this frame to this frame, you have to apply this transformation and this rotation. That's it. There's nothing more to it. Okay? Bear in mind that if you do it again, you have this, for example. If you do, for example, I don't know, 3, it publishes 3, you get 3, and you see we are getting the 1, then the turtle 2, and then again the turtle 1. So they are published sequentially. Okay, so let's stop this. These crazy turtles. There we go. So we have this other method, and we also have this ROS run TF echo. This is even more useful because it gives you the transform between turtle 1 and turtle 2. If you have a look to the TFs that were published in the TF topic, you see that they are not published, the TF between turtle 2 and turtle 1. Why? Because they're not real. They're not published. This system, the TF echo, what it does is make the transform using the TF3 that we saw here. Yeah? So what it does is connect this turtle to that turtle. Like this. Understood? And what it does is, if we start publishing again, and then there we go, and it starts publishing the transform. So what's this information? Basically, it's the same thing. It's the translation and the rotation in quaternions, and in radians or RPI, so roll, pitch, and yaw, in radians and in degrees, or in quaternions if you like. And basically, it's because they are aligned, it's only a transform minus 0.6 in the x axis. Okay. But this is not the best way. The best way of visualizing the TFs and knowing what they are is obviously using RViz. So let's have a look. So if you go to exercise 3.4.1, you'll get the RViz magic. So let's do it together. So the first thing, of course, we have to publish the TFs. Nothing special about that. Let's move the robot a bit, the turtle, just a bit, so that, there we go. Okay, I'll leave it here for now. Now I'll publish the iRobot. Okay, he's going there. I'm going to start moving now the turtle. Okay, let's do circles, more or less. Yeah, very good. And then, so more or less the world is around here, the world frame, and then we have the turtle 1 and the turtle 2. So let's have a look. So ROS run RViz. Again, we have to go to the graphical interface. And there we have it. So here you have a 3-dimensional representation of the frames. So world, and then the turtle 1 and the turtle 2. Let's have a look a bit closer. There you have it. Turtle 1, turtle 2, and you see how turtle 1, it's doing circles around turtle 2, which is trying to get it. Okay, so more or less it would be this. Yeah, more or less this view. More or less, yeah. Okay, if you didn't get this, don't worry, it's because you didn't add the TFs. So let's get rid of this that we don't need, and you just have to add a TF if you want when clicking add and then TF. That's it. And then inside it you have to select, let's activate it first, so it gets the TF topic. Then you have to select the frame, which in our case we only have 3 frames, and that's the basic, the fixed frame. If we change it, for example, to Turtle 2, then it changes completely, because now Turtle 2 is the fixed frame, and then it's turning Turtle 1 and Turtle, it's more or less fixed, the distance, because they're turning, and it's the world that it's turning. Okay, but there we have it. Okay, fantastic. Yeah, let's save the changes. Okay, fine. So that's it. You should now have a basic understanding of how the TFs work. What are the TFs? And very, very important in ROS, how to debug and see if it's working. If you're publishing, what data is it publishing? Is it coherent? And I really like the RViz view, because you get the idea of what it is exactly, the TFs, which are basically frames moving around based on other frames, referred to other frames. That's it. Okay, so you know the TF basics. So now we are going to, first we're going to stop this movement. Yeah, okay, perfect. And we go to the next chapter. Fantastic. So now it's your turn. Now you have to create your own publisher, your own, what in TFs we call broadcasters. The TF publisher, it's called broadcaster. The TF subscriber, it's called listener. So let's create our first broadcaster. So here you have an example of how to do it. This one is essentially the one that publishes the frames of the Turtle 1 and Turtle 2 based on, referred to the world frame. So I'm going to talk a bit about the code and what it is and how it works, more or less. So first things first, when you launch this Python, you'll execute this method here, which initializes the node. This you should know it by now, for its ROS basics. You have a list of the robots that you want to publish, and then I use this gazebo model that we'll use afterwards to get other stuff. You'll see in a moment, just in a moment. So, what do we use this? Well, you'll need in your system, you need a way of knowing the position of the robot. It could be odometry, it could be navigation systems, it could be GPS. In this case, because it's a simulation, we use this gazebo model class that we generated that what it does is extract the exact position of each model in the 3D space. So we know exactly, our simulator gazebo knows exactly where this turtle is and where this iRobot is at all times. So we use that as our source of data or to position our robots. But it could be other stuff. Or if it's an articulated robot, then it won't be a position, it would be just encoder reading, for example. And this applies for real robots and for simulated robots. For ROS, he doesn't care. Okay? Understood? So in this case, we're using this class that extracts basically the position that we have. Yeah? We're going to publish each position for each robot, and we're going to publish the TFs with this method here. Essentially, it's a while loop that gets the position for each robot, and it publishes the TF. Nothing special about that. This handle turtle pose, it's here, and here it's the core of the TF broadcaster. So we generate this class TF transform broadcaster, and we use this one to send a transform, which basically is we use the position and we give an X, a Y, and a Z. This is the position. This is the orientation, which is in quaternion format. Then we have to give it the time right now and the robot name, which will act as the frame, the name of this new frame that we're publishing, and then the parent frame, in this case, world. Yeah? That it has to coincide, obviously, with the frame in which you took the data from. And that's it. It's actually not that complex. So I give you as exercise here, exercise 1.1. So in this exercise, you are going to create your own first TF publisher to publish the position and orientation of both Turtle 1 and Turtle 2. So the first step is obviously stop any publishers, because otherwise you won't know if it's working or you'll get mixed readings. So the first things first, you have to check that you don't have anything published. In this case, we're going to check no, 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 and no. Okay. Then, next step. Well, the next step is you create a package that depends on ROS by and Turtle TF 3D, which is a package that we generated for this simulation. Essentially, you need it because you are importing this class, a gazebo model, from this package. Okay, fair enough. Once you have it, then you create a Python script that contains more or less this data, this example. You can change it, you can do whatever you want. You have to be sure that you're publishing in the right frames and with the right names. Okay, and then you run this Python. So I have it already. I created a package. In my case, it's called your package. And inside it, I have this multiple broadcaster, which is the code that we just saw. So ROS run, name your package, multiple broadcaster, and we start running. Nothing happens, of course. We are just publishing the TF. Then we're going to launch it's already prepared for you, which is the listener. This, if you publish correctly, it will start listening, and the iRobot will start to do the same thing that it did with the global launch that we've been launching in the previous unit. Yeah? Once you have it, let's have a look. Let's see what happens. I don't know. You can, for example, do an RViz. You can do anything you find. For example, let's see, ROS run. Look. No, sorry. tf3, and I'm going to generate the tree in this case. And we have it here. It's working. This is one test, fast test of now if it's working or not. Okay, we're going to stop the iRobot. Let's, for example, do another thing, do another exercise, which is let's publish the Coke can. So how can you do it? You have to modify the code so that it publishes also the Coke can. You should have something similar to this when you finish. So let's have a look. I have it already done here. So I have a publisher that publishes both. So ROS run your package turtles. Okay, we're publishing. We don't need to do the listener, it's just to test that it works. So if we execute the RQT tf3, we wait for it, and here we have it. So we have the Coke can referred to the world, also the turtle 1 and the turtle 2. That's what you should have. And it has to update the time indexes. Okay? Otherwise it's not publishing. Perfect. Great, I hope you did manage to do it. So now we have to do the listener. We have to create the listener that moves our robot. And here is the example of how to do a listener of TFs. So we'll start from the beginning. This, what it does is we initialize the node. We initialize this listener class. It waits for three arguments, which is the turtle listener.type, but then 2 extra, let's say. You have to give the follower model and the model to be followed. And with this, it takes those names, and then we have a publisher. We generate a publisher for the command vel to move the corresponding robot that we just told him that it's the follower. Then we initialize the rate and some other variables. Here we define an on shutdown callback, which will be called when we Control C. And then this is the important part for you. It's we try the listener that gets the transform from this frame to this frame in this time. Yeah. If it doesn't, then it will try again. And basically this gets that data and publishes the command and makes the robot move. Let's have a try. We have the listener here, so we're going to publish, for example, let's publish, we have it already here. So ROS run, in my case is your package, then the listener, then we say turtle 1, it's the follower, and turtle 2 is the one to be followed. So as you see here, now the one that tries to follow is the turtle. It's the one that it's trying to follow the other one. You see, so it got on top to get exactly the same position and orientation. If we stop it, it will stop moving. Okay. So I think we have it. So we have this listener. Here you have some explanation, more detailed, and more or less how it's doing the navigation to get from this to this. For example, you can try to make it that the listener follows, let's say the turtle one goes to the Coke can. So let's have a try. Let's see if it works. So it's Coke can. There we go. Whoa! Went super fast to the Coke can. And there it went. Stop it. So now it used the TF that we are publishing here of the Coke can to make the calculations to know what orientation and what speed also, because it's proportional to the distance it needed to get to the Coke can. Yeah? Okay. Then adding more frames, and you say, oh my, do I need this? Of course you need it, because normally in robots you need, let's say, tenths, like a tenth of frames, or you need 20 frames for each. Let's say you have two cameras, you have arms, you have legs, you have a laser system that you need to have a frame there, anything. So you have to publish there. So to add more frames, you just have to use this simple code, which is basically what we used. It's more or less the same. But in this case, we are doing a fixed transform. A fixed transform is used for cameras, for example, that don't move. That's one of the main applications of them. Or you can publish something that it's moving, of course. Yeah. So give it a try. I won't do it. It's more or less the same. And then you have here very interesting, very useful information, which is how to go from quaternion to Euler and to Euler to quaternion, which you'll need for sure. Yeah. And last but not least, add more frames, as many as you want. Experiment. Make, for example, this turtle to follow a frame that it's moving in this one. So you'll see that it moves around it, but not to it, but around it. For example, if you have a frame here that moves, then it will follow that one. For example. Yeah? Okay. So here ends the first part of the TF, how to use TF on ROS 101. The next part will be how to use state publishers, how to use them to publish very complex TFs. Okay, so welcome back again. So why do you need a robot state publisher? As you may have noticed already doing the exercises, it's really difficult and really tedious to publish 1, 2, 3, 4, 5 frames. Imagine this. Imagine the TF publishing of the RoboNav 2. Look how many frames. It's impossible to do it manually. It's impossible. And not only that, but what happens if they change the hand? What happens if they change the length of the arm? Or the distance between the head and the neck? What happens? You'll have to change all your code. It's impossible. So ROS has our back covered because they created this tool that it's called Robot State Publisher. And what it does is publish the TF based on a URDF file. You give the URDF file defining all these joints, the head, the arms, the fingers, and automatically it publishes the TF. Nice, huh? So, how are you going to learn this? Obviously, we're not going to use the robot nout because it's not that it's more complex. It doesn't have the number of joints is not that big in comparison with the PyRobot, but it has a very complex and rich robot description. It's really complex. It has a lot of plugins, a lot of files, and this PyRobot, on the other hand, has only one file, and it's all the things defined there. So it's much easier to understand, but it's the same principle. And if you understood this one, you can do any robot state publisher of any robot, of your own robot if you want. Yeah? So let's get started. So first things first. Let's have a look. How does this work? So the first thing you have to notice is that you get the PyRobot and it's wiggling around its arms. That's because it doesn't have any controller, and there's no air friction here, so it will just swivel its arms forever and ever. Yeah. Okay. So let's start the controllers. So here we have it. Okay, here we have it. We launch it. It will start the controllers. Now it stopped. It stopped as it is, so it activated the controllers with this ARM configuration. No problem. But now it's rigid, so it doesn't move. Okay, fair enough. Let's publish something. So what we have here, when we activate the controllers, are a series of publications of the command. So here you have to publish any command and it will move the arms. Let's check it out. For example, we can tell it to move. In this case, it's the head tilt joint. There we go. Wait, it moved up. Then we can publish another one, for example, this one. Okay, it moved the head, more or less. There we go. Perfect. So you have to get movements more or less like this. Let's have a look. Let's have a look how the TF is configured. How complex is it, or is it simple, or let's have a look. So I really like the RQT TF3, so I'll go with that. But you can try any. Let's have a look. There we go. Wow. Okay, this is not as easy as the other one, huh? You have all the structure here. Let's have a look. Maybe let's generate some frames, a PDF, so we can have a look at it easily. There we have it. Let's download it. I'm going to have a look. Wow, okay. So as you can see, it's much more complex. You imagine doing this manually? So there we have it. It's the world base. So the world, then we have the base link, we have the base laser, CPU, then we have the torso, which divides into 3, which is the head, the left arm, and the right arm. And that, but one of the useful things about it is that you have a very good idea of the morphology of the robot just watching the TF tree. Okay, so you can see, for example, also if you do it in the RViz, you'll get all the articulations, all the TFs, and so on. Yeah. So the first thing is stopping everything, and then we'll launch this simple robot state publisher. Bear in mind, what are we doing here? We are loading to the robot description param this PyRobot version 2 URDF, and we are initializing the robot state publisher. That's it. We are not doing anything else. Okay, let's have a look. Let's execute and see what happens. So we are going to create a file, which is a simple py, for example, .launch. Yeah, and we are going to copy this. And we execute it. ROS launch. Whoa, sorry. First we have to do something. We have to stop the controllers, because this system executes, starts the controllers, starts the state publisher, and starts other stuff that we are going to talk about in a minute. So let's ROS launch your package, simple py launch. Let's have a look. I'm going to, for example, generate, I could generate the frames, for example. For example, let's go to the let's, for example, execute this ROS run RQT tree to see what happens. And let's have a look. Wow, this is strange. You see, you don't have them connected. None of them are connected. Why? Why aren't they connected? You see, you have the left shoulder, a blink, so on, blah, blah. But we don't have the marvelous tree that we had. Why? Well, there are a pair of reasons. So we're gonna have a look to the code. What are we doing here? We are loading the description of the robot, and we are publishing the robot state publisher. The robot state publisher, it's only publishing the static transforms, so the fixed links. So any connection between all the links in the PyRobot that depend on variables, for example, the elbow or the neck, the robot state publisher doesn't know, because it could have any value, and that's why the TFs only are published the ones that are fixed. For example, the transform between this joint and the head, it's fixed, it's the same one, so it's published. and so on. And then you ask, how do we solve this? Well, we solve it in the same way as you would solve it in a robot, in a real robot. To know where all the articulations are, you need encoders, you need sensors that read the position. And here is where the joint state publisher comes into place. And you have to publish it. Okay, let's have a look. Here you have an explanation of why this happens, but you see here, this is a fixed. This you can see it. But this one is continuous. This is a joint that is continuous. It depends on where it is. So we need to publish the configuration of this joint, which is headpan joint. Otherwise, you won't be able to publish the TFs because the TF has to know the exact configuration of the robot. Articulations, all the joints, how they are, and all the fix. The fix he does know through the URDF file. But the joints that aren't fixed, it has to get them from somewhere. And that somewhere is the joint state publisher. Next step, let's publish those joint values. And you say, okay, but then we need encoders, we need the controllers to move them in a certain place and that they stay in the same place. You're right. What we're going to do is publish only the joint states. What effect will that have? We're gonna find out. So let's stop this, and now let's launch this one that I had prepared. I have this one, which is basically the example that you have. Here we are loading the description. Okay, so all the fixed joints are covered. Now we publish the joint state publisher. We start it. Yeah, we start the GUI, let's say, and then we publish it. We publish the robot state publish, the robot state publisher, and the joint state publisher. The joint state publisher will publish the joints, and the robot state publisher will publish the TF. And then we start the RViz with certain configuration. So let's run ROS launch, your package, and Pi robot in this case, and we launch it. Okay, so it started some stuff. Oh, there we go. Okay. So we have the base link, which is this one here. And then we have this GUI, which allows us to change, to publish into the joint state topic. This way, now you can move this. Not only that, but you see that the TFs move accordingly. That's because now we can calculate the TF. But wait a minute. Let's have, I want to show you something. For example, I moved this one to the left, but the robot doesn't move. I'm going to something, for example, the elbow joint. Let's, the right one, put the elbows, the hands up. It doesn't move. Why it doesn't move? Because the controllers aren't activated. It would be the same thing with a real robot. What we're doing here is publishing, let's say, the encoder readings, but we're not publishing anywhere to move the robots. We're not using the drivers of the robot to move it and to read from those joint states so that it moves the elbows, the joints in the way that matches that value. So for now, we only have the TF published and the joint state published also. Understood? So here we have it. what do we have to do? Now we have to execute the joint states through the controllers, not through a GUI that publishes fake, let's say fake joint states, because the state of the joints is not the one shown here, but the one here, because this is the real robot. Okay, so let's stop this. Let's check everything's okay. Okay, and now let's go back. Okay, I'm going to talk about just a little bit of how you define controllers, because you'll have to do your own robot, so you'll have to know it. I'll give you this example. You have this example here. You have this joint that it's called left shoulder forward joint. It's a revolute, which means that it has a lower and an upper, which is quite understandable for a shoulder. It could be continuous also, like it could be, for example, the torso, it's continuous because it can spin around with no problems. But for example, the elbows, it's physically impossible that they turn 360 degrees. So we put that limitation. So that's why we use the revolute class here. And we define some data like dampening and so on. Then this is all defined in the URDF. Below it, you'll have to define a transmission, the motors that move that joint. So you'll have to give it a unique name. In this case, transmission 4. And the actuator name also, it has to be unique, motor 4. Then you have to specify the type of hardware interface, in this case is effort joint interface, and the reduction. Okay? You also have to specify which joint is moving. Perfect. Then, once you have it, you have to define a YAML configuration file, which has this basic configuration, let's say, morphology, sorry. And here you have the name of the robot, normally the model of the robot. Then you have this always joint state controller, at which hertz, at which rate you are publishing all this data. And then you define, okay, a left shoulder forward joint position controller, which is essentially the name of the joint that we're controlling plus the position controller. And then you define the type, in this case joint position controller. You can control position, you can control with effort, with speed, but in my opinion, in my experience, the joint position controller works pretty well. Here you define the joint that you're moving, and very important, the values of the PID. This is a default. It could be, you can change them if you want it more fast, if you want it to oscillate, if you want it to go slower but more exact, and so on. It's PID theory and control theory, which we're not going to talk about here. Okay, and then you start the controller. So you load this YAML with all this configuration parameters, and then you start the controllers, which is in this package, this program, this binary, and we put some data, and especially we put the controllers. Okay, X1 controller, X2 controller, the names of the controllers that we're using, which are these, the ones that you stated here in the YAML. In this case, it's 1. Here we've put some more examples, and you also have to put always the joint state controller. some errors that could arise are here. So once you have it, you will be able to move the robot easily. So you can do it as we talked about at first in the first example that we did, or you can do it through a GUI, which is much easier, and you can do movements, more complex movements. For example, we can, let's go here, sorry, there we go. So I'm going to execute the controller, the basic one, which is here, the Pi robot controller, which this one, what it does is publish everything. So the robot state publisher, the joint state publisher through the controllers. Okay, all set up. Now we can go here and let's have a look. Let's have a look. Oh, there we go. Here. So ROS run RQT GUI. For example, in web shell number 4. You'll get something like this. You have to select topics, message publisher. Then it updates, it gets all the topics that you have available in your system, and it will get, among other topics, it will get the command topics for each joint. So you can write here, for example, you can select also, but I think it's faster. For example, left elbow. For example, you state the hertz, publish rates, and the type. You just click to add it, and then you can put any value you want, or even math Python formula. And I, it's a time, it's a variable that evaluates to time, and then 100, for example, and then you activate it. So we have the robot that it's not moving, we activate it, and it starts to publish on that command and start to move. Okay, and you say, okay, what does that? Now if we have a look to, for example, the RViz, ROS run RViz, we go here, let's get rid of the names, and we are going to scale it a bit, 5. This way the are a bit, there we have it. So we have the robot. Let's add the model. For example, there we go. And you have it there. So now, I want you to understand what's happening here, because a lot of things are happening here. We are publishing the TF because, and the TF knows exactly all the positions of all the articulations, because not only knows the fix, which he reads from the URDF, but also the ones that are not fixed, because you are publishing into the joint topic, joint state topic, and in that topic it's published by the controllers. That we, in the demo, with the sliders, we did it with a slider, but now it's the controllers that are publishing everything. That's why this now corresponds to this movement without any problem. Okay. And there you have it. This is an example of how to, I think, here is more or less how to create your launch file that I just executed. And here you can do exactly the same thing as I did. Okay, you generate your launch, and you'll have this moving exactly the same way as it's moving here and it's moving here. I just launched the default one, but it's exactly more or less the same. Yeah, and we're going to talk about the code then. So again, we publish the URDF in this robot description param, then we load the YARN configuration, which has all the controllers defined. Then we load the controllers, which you see you have loads of them because you have one for each joint. So the headband, you have right shoulder, you have the elbows, and so on. And finally, we run the robot state publisher. You see, we're not talking about the joint state publisher anywhere, because this one is the one that publishes there. Okay? Very good. So congratulations. If you've done that, you are ready to create your own robot, to move it, and to publish the TFs. So well done. Now there's only one thing left, very simple, and then we'll go to the micro project. So, welcome to the last unit before the project. Well done if you understood everything. You are more than capable of using TFs, publishing, subscribing, using the robot state publisher and joint state publishing, also knowing more or less how to do use the controllers to move a simulated robot in Gazebo. So very well done indeed. So last but not least, we are talking about static transforms, which essentially is this case. You have this robot which possibly you're using robot state publisher to publish the TFs, but then you have this camera, and maybe you move it here, maybe you have it here. It moves, or maybe you change it, and you change it quite often, and so on, but it will stay there forever and ever once you put it there. This is one of the cases where it's very useful to use static TFs because it's something fast. You use it, you publish it, and that's it. You don't have to publish, you don't have to generate any Python code that publishes it, because it publishes once, that's it, you have it. You can do it in two ways. In three ways. You can do it as we talked about in the first chapters, which is doing a Python code and publishing a static transform. No problem there. But then you have two more ways. One is through the command line, and the other is through a launch file, which essentially is the same thing. What you're doing is using this static transform publisher, and you publish the XYZ position and the yaw pitch roll orientation, then the frame ID, the child frame, so the frame, let's say the parent frame and the child frame, and then at what rate you publish it. Practical application. Let's have a look. We have two turtle bots. Both of them are publishing their own TFs. Why? Let's have a look. ROS run, for example. Let's have a look in RViz. ROS run, RViz, RViz. Let's take a look at, for example, the robot odometry. There we have it, robot 1. We have also publishing, you see, we are publishing also the robot 2 data. So for example, let's get the robot 2. Okay, but we don't have the other one. Why we don't have the other one? Because they are not connected. How do I know that? For example, let's execute ROS run TF view frames. Okay? Oh, sorry. ROS cd source. Let's download this. Oh. Okay. Well, this is a quite complex one here, but you see quite fast what happens here. So we have the robot 2 and the robot 1, but they're not connected. Everything else is published, so it's published all to the base footprint and blah blah blah. Why? Well, basically this is a robot that doesn't have any moving parts, so it's really easy. But they're not connected. That's why we can't publish the same TF, so that the TF of both robots at the same time, because they're not connected. So ROS doesn't know how to do the transform from this Atom frame to this one. So it can't represent, for example, this element from the robot 2. Robot 1, it can't publish this element from robot 1 in to this one in robot 2. It can't, because it can't go here. It's not able to make this jump. So how do we do it? Very simple. In this case, we're going to publish a static transform between the Atom frames. Why? Because the Atom frames are the same and they are fixed. And so if we transform and we generate a static transform between them, we'll automatically connect them. Okay, so let's do it. You have here, you see, we don't have it. So now we can publish here, for example. Let's try it here. Okay, I think it's publishing. Yeah, immediately we have it connected. We have them connected immediately. Let's get out the names and the arrows. We don't need them. Oh yeah, we need them. Yeah, let's put it. So we have now, we got them connected. If you don't believe me, let's do a ROS run TF, yeah, view frames. Again, ROS CD, we have to do it here because otherwise we won't have access to it. CD, source. We are generating it. And we download it. Whoop. You see, you can see it now. So here we have both connected. The only problem is that it's really big. But here you see, this one's the Atom one, and here we have the Atom from the robot 2. So they're connected. Perfect. So now you can move the robot around, for example, ROS topic publish in robot 1 command vel geometry twist, and we make it turn and move around. Whoops, sorry. This one's not there. There. Example, and we publish, we make him, for example, this one move really slow and turn fast. There we have it. So we have them both moving at the same time, and you see here we have one moving and the other one moving also, and they are based on this Atom frame, which is the same one. Okay, so we have them moving around. So fantastic. So this is an application of how to use the TF static transform to solve a problem of connecting different different robots and have multiple robots. We were able to do this because the autumn frame was the same one. Yeah, refer to the same place and fix. Yeah, great. So let's go to the micro project. If you got to this far, congratulations. You know all the basics of TF to work with it and to debug it. Fantastic work. So now, as a challenge, as a way of learning and interiorizing all the things that you've learned in this course, we propose here a micro project, which is creating your own robot as the Pi robot that we used in the Robots Day Publisher exercises. Do one similar to it and publish the TFs and make it move. So some things that you might want to know to do it. So here you have an empty simulation. You can create your own packages here, and in those packages you can do launches that spawn models. How do you do that? Well, here is an example. So here you're giving it a position, in initial position, and then you're getting a URDF that will be loaded in the robot description, and then you spawn it in a place where you want. Yeah. Let's have a look. I have an example here already prepared. So here the spawn robot version 2, which it will spawn there we have it. In this case, it spawns our little old friend, the Pi robot. Okay, now, what if I made a mistake? What if the robot doesn't work? The way is you can remove it. You can remove it from the simulation. You just have to see what's the name. In this case, you have the ground plane and the Pi robot in your world. And now you have to delete it. So you use also another service that deletes the models that you give the name of. For example, in our case, we have Pi robot. And there you have it. So in this way, you can develop your own project and your own robot. You have here some guidelines of how to do it. You have an example of the Pi robot URDF as template. So if you So if you go to this ROS CD Pi robot package, you have the URDF that we used for spawning. So you can copy it to your workspace. For example, let's copy this Pi robot version 2, and we copy it to your workspace, which is home user and catkin workspace source. Okay, for example, and it will appear automatically. I just wanted to go faster. So there you have it. And here you have all the code. So you have all the system defined, the materials, the joints, and the links around here, and also the transmissions, of course. You can select the syntax. There you have it. So you have an example of how to do it. Another example, very fantastic example, is the R bot Git, which is magnificent. It's very good, and you have a more complex example with multiple URDFs using chakras and so on. My recommendation is that you first start with the PyRobot example, and when you want to make your code cleaner or maybe modular, then go to the RBot example. And then some recommendations: add some cameras, some lasers, be crazy. And please, if you do something that you're proud of, send it, upload it to the community, send it to us. We will be delighted to know what strange and fantastic robots you create. And that's it. So thank you a lot for staying to the end. You're a machine guy or woman, so very good. So what to do next? So the natural step would be, okay, I want a more open environment to develop in. So obviously you can do it locally, but you have in our ROS development studio, you have plug and play simulations that you can start working now without any hassle of installation and so on. And very cool simulations, I must say. So you can work with drones, you can work with BB-8, robot arms. You can use other simulators like, for example, Weebots. If you're more into, okay, I want to learn more, so go to Robot Ignite instead of going to the ROS Developmental Studio. Go to Robot Ignite and learn about navigation, learn about OpenAI, learn about maybe the ROS basics. You don't have them very clear. You can also try our exams to certify ROS. What's your level of ROS? And that's it. Thank you very much, and we hope to see you soon.